A viewer commented on another video inquiring about performance, and I thought it'd be a good idea to discuss the current performance levels and various ways I improved it. Hi, I'm BGK of Pear Tree Games, and this is Return of the NVIDIA Devlog Interlude, Performance Optimizations. Before we begin, I'd like to mention that the NVIDIA project uses Unity 2021.3 with the built-in render pipeline and currently gets about 200 FPS in editor and closer to 300 in builds. I shouldn't even have to mention, but check your profiler before you start optimizing your own game, and these techniques are specific to my game, but hopefully you can get some idea of how to improve your own. Okay, so in general, I like to think about performance as trade-offs between processing and memory. If you have processing issues, you can try to unload some of that into memory by pre-processing calculations, which is a common technique that I employ. We'll start with the ocean. Each block is moved in a vertex shader as individual game objects, and not a single mesh. I did try that, but couldn't get it to work in the style that I wanted. But having tens of thousands of game objects load with your scene is ill-advised. Instead, all of the blocks shown in the editor are cached into sections as scriptable objects as two arrays, one for their position, and another one for flows, or the distance to the train and river block. For that, we get all the terrain blocks at height 0, and then using the jobs and burst system for every ocean block, we calculate the nearest distance to a terrain and river blocks. Then, during the build phase, I delete the entire ocean in each scene. During runtime, our Ocean Manager preloads a bunch of sections using addressables that are near our player in a slow update. Then uses our camera frustum and object pooling to move ocean blocks to the desired location and set the appropriate flow values. We get the benefits of Unity's dynamic batching, but unfortunately we still have a large number of shadow casters, which is an issue I haven't been able to resolve quite yet. Next up is the terrain. Using the blocky editor, I place a bunch of game objects down in sections. Then, once I finish painting, the blocky editor will automatically merge sections using the Asset Store's Mesh Combine Studio 2. This will convert thousands of static game objects down to a couple dozen, reducing draw calls dramatically. I also combine colliders where possible, though I'm not actually sure if that's necessary since Unity is pretty good at optimizing its physics calculations. Then again, during the build phase, we delete all of the original game objects. During runtime, we assign each mesh a bounding sphere in a culling group and enable and disable the meshes on visibility, shown here by the purple bounding spheres that are disabled and the yellow ones that are enabled. I don't use the built-in occlusion culling because I found it difficult to get these settings right. Shadows would pop in and out too much, or objects were never removed. It's not perfect, that what I have, but it works for my needs. One other thing you'll notice is that the world is partitioned into these grids that are streamed in and out depending on the location of our player. This makes it easy to keep all of our objects and all of our calculations down to pretty minimal levels. Another area which I optimized, which was a small thing but actually was causing quite a bit of issues, was the light flickering. A standard way of dealing with flickering lights is to use a queue of intensity values and average them out every frame. This is fine for some lights, but when you have dozens or hundreds, it can really tank your CPU usage. So instead, I store all of the lights in each scene under a light manager. This then adds all of the queues together into one native array, storing the starting index and queue length. Then we can process all the lights in parallel using the IJobParallelFor interface. If interested, here's the code for that job. I also allow for time-dependent values so the lights will only turn on during certain hours of the day. Lastly, a tool that I'll mention is the more effective coroutines. It reduces garbage created from coroutines and also provides an add-on to easily transfer your running coroutines to another thread and back, which is something I use for pathfinding. I have to cache the pathfinding points so we're not dealing with game objects directly, as you'll see here. And we can even debug that info. Each point is stored in an array in a scriptable object with some info about the tile. And then we only load that section when we need. So to recap, reduce draw calls by either combine meshes or use static or dynamic batching. Cache objects as asset data and then delete them from the scene and use object pooling to instantiate them instead. Use culling groups if possible for distance or visibility checks. And use addressables to easily manage, load, and release assets. Use jobs and burst systems to execute CPU-intensive tasks, or multi-thread calculations if game objects aren't involved and you can avoid the main thread. So I hope you found something useful. If you have any questions or want more information about anything, feel free to comment below and I'll share what I can. Thank you for watching.